Thanks. I think we're, oh, no, we're not there. Almost there. Any questions at the moment? Okay. Well, welcome back, everyone. We got through our third exam. The summary statistics are posted up above as well. And the solutions, if you'd like to take a look at them, they're also posted right here as well. So the average came out to 76.1%. The maximum was 92.9%. So this one was definitely probably the tougher one out of the whole set. We look at some of the historical statistics. I already kind of forgot what they were at. Exam 2 had a maximum of about 97% and an average about 78%. So I think the maximum took a bigger hit on this one, but the average was still pretty stable. Any questions folks have about the exam? Any problems on there or things along those lines? Okay, yeah, go ahead.
Well, we're going to be on any further exams? Very last problem.
Sorry, say again.
The very last problem going to be on any further exams?
Well, that's a good question. Let's take a look at that thing.
That one's gnarly.
That one was gnarly, yeah. What made this one kind of tough was the constants we had to navigate through on this thing. So something like this won't be on the final exam, but you could expect to maximize or minimize some kind of optimization problem. So not necessarily of this kind of context. We did one that had lots to do with context, so constants here. So it'd probably be a different theme on the actual one on the final exam. And now that you mentioned the final exam, I just want to throw out there that they gave us the official time, room, and date finally, just today. And for the final exam, we'll be doing something slightly different for the review problems. I'll still put out that mega huge set. Now it's going to be problem 1 to problem 100 or something like that. Really, really long file. But also be uploading the old final exams. So you'll see what it looked like as a final exam when it was all the prior semesters. I should have several of them posted here, so you can use that as an extra resource to study coming up. But other questions, folks, on this one? Oh, wrong one. On this up here? Okay, just for a quick run through of what happened on this thing was, it was all about the constants. They're pretty tough to navigate through on this problem. When you differentiate the kxn term, x goes away and you just get the kn. Derivative of negative kx squared gives you negative 2kx. But then from here, solving for x gets you to n over 2. So the contagion, whatever it is spreading the fastest when it's inflicted half the population already. But honestly, the hard step is right exactly here. Calculating that derivative was the hardest part about this whole problem. If you got through it once, you could get through it twice. Second derivative is always negative. And so the second derivative test tells us we have a maximum right at n over 2. So it looks fast if you see it on paper like this, but it was not a fast problem. I agree this one was tricky because getting just to the first derivative alone, unless we had a really careful eye on this constants, was not easy to get to. But that's why we practice this kind of stuff. This calculus concepts is really all about these kinds of things. And so if you're taking more calculus or taking an engineering class or a physics class, chemistry class that uses this kind of stuff, your derivatives are probably going to look more like this than you've seen in our actual class. So that's why there's lots of this kind of stuff thrown in there. But other questions or comments at the moment? Yeah.
The high value limits on like
Oh, I think depends on how it would look there, but let me take a look at that.
That's a good question.
Not sure why.
Gotcha. So right when you go to here, you're plugging in x equals 2 in that location. But once you plug it in, you didn't necessarily have to write that statement again.
So when plugging the value.
Exactly, yeah.
Okay, thank you.
You betcha.
Other questions so far? Okay, well, we got through our third exam. So where we're at so far in the course is we're going to take a look at section 5.3 once more. 5.3 is definitely an important section, and well, it says the fundamental theorem of calculus. So that's one of the sections where you can expect these techniques are going to be used essentially everywhere. Whether you're taking Calc 1, 2, or 3, we have to be very familiar with these techniques. So before we get started today, we're going to go to section 5.3, just practice doing some more integration for a definite integral. Then we're going to take a look at some more indefinite integrals. I don't intend to finish off these notes today. So really this week, think of it as kind of a warm-up and then 2 sections. So it's going to be kind of a lighter week, and I think we deserve it. After that, we'll take a long deserved break. Other questions or comments at the moment? Okay, well, let's get going then. We're in section 5.3, and here's how it starts. We're using the fundamental theorem of calculus part 2. And what this provides us is an extremely fast method for finding the area under the curve, the sine area, which is what this is indicating. We want a definite integral from a to b of f of x. Let's just draw a quick figure just to see what's going on. It's the fundamental theorem, so it deserves a bit of an illustration. Let's say this is our a, this is our b. Our function f of x could do something like this, for example. Let's let it dive down and come around like that. Now, when you're integrating the function from a to b of f of x, the only thing I could tell you for sure on this problem is what the sign of the area ought to be. Anyone can tell so far, should that be a positive area or a negative area? I agree, absolutely. The illustration here is we make a couple line segments. In this region, all the area is positive, but here we have loads of negative area, so it's definitely going to be negative altogether. Then the fundamental theorem says you don't have to use those area arguments that we've been using, which are not easy to do by hand, and we did them by hand. Instead, you can find an antiderivative f and just say that the area which is negative in this problem is just going to be equal to f at b minus f at a, which is typically expressed in this way. We take an antiderivative of f of x and evaluate it from a lower limit of integration to an upper limit of integration in that way. So think of this as like an evaluation bar. I usually write it as a bracket. That's a habit. Sometimes you see it as just a bar segment. So really a stylistic choice, however you like to write it down. I think that's the better one because it reminds us of Leibniz notation when we put an evaluation symbol on it. So that's what we're trying to calculate, and let's give it a try on this function right here. First, any questions about the theorem at the moment? Okay, when we take on this question right here, we have to be very, very wary of this. If we were differentiating, we would not differentiate the numerator or denominator. The only time we ever really did that was Leibniz notation, or excuse me, not Leibniz notation, L'Hopital's rule, getting my words mixed up there. For this process, we definitely need to simplify everything we see inside the integrand. So it's going to start by being a definite integral from 1 to 2. Let's fix the denominator first so we'll know what we're dealing with. It's the 7th root of x power 8, but a 7th root just gives us a fraction. That's the denominator. So take x to the power of 8, divide by 7. The numerator had power 3, but it'd be nicer with a denominator of 7 on that power, so you can bump it up to a power of 21 sevenths. So we're back to the same exact problem. We didn't change anything fundamentally about the algebra, but now in this format, we can subtract the exponents. So this is the definite integral from 1 to 2 of x to the power, let's see, take 8 away from 21, and we're now down to 13 sevenths. That's a strange exponent, but that's completely fine. The fundamental theorem doesn't care how weird our exponents look. Dx. So we're at the process of having a nice integrand to work with. That's the function f of x right there. All we need to get the area, the signed area under this curve is just a really handy available antiderivative. And this word is really nice as well. It gets a little bit confusing when we're doing an ordinary antiderivative, what we'll soon call an indefinite integral, because when we do those, we add a constant of integration. But the constant of integration for definite integrals like these make no difference. So we really find any antiderivative, we take the simplest one, we just don't throw in a constant. So here's how it goes. We're producing the function f now. X has a new power. It was 13/7. Any volunteers for what it should be after taking the antiderivative? Exactly, we're adding 1, which is a 7/7 to that thing. So it's 27. Always a good call to put a little bit extra space. And visualize dividing by 27 says just multiply by the reciprocal, 7/20. Once you get to this stage, we have the antiderivative, but definitely eyeball it or grab some scratch paper, visualize what would happen if you did differentiate that. We have to come back to here upon differentiation. Let's do it out here just on the notes this one time, but you're okay to do it mentally as well. If you did differentiate that function, it would be 7/20 times. This exponent will come down as a coefficient, so it's 27. We subtract 7/7 from that thing, so now it's 13/7. At this stage, I'd be convinced. All those constants are canceling off. That's why we divided or multiplied by the reciprocal of the exponent to make it work out. And we're right back to x power 13/7. So with that step out of the way, we'll put down an evaluation bar. And sometimes I like to put a bracket on it, but that's completely optional. We're evaluating the whole thing from 1 to 2. So lower limit, then upper limit. And there is one small extra trick on here that doesn't work on every problem, but sometimes it's valuable to factor out this constant, especially if it were a negative sign. If it weren't a negative sign, if it's just 7/20, this step saves a little bit of writing, but it can make your work a little bit more clear. You can think of the evaluation as happening only on the thing that involves x. I'm leaving 7/20 factored outside, and it turns into 7/20 multiplying the result of first putting 2 right where this x is. So it's now 2 to the power 27. There's always a minus right here. A lot of times, even when we're really fluent on this, that negative sign is easy to miss. So that's highlight worthy, I'd say, on our first problem. Let's highlight that one as well, why not? Then take your lower limit of 1, plug it back inside x. 1 to the power of 27 is still 1, so I'll just write that in as a 1. And then the whole problem stops right here. We have a positive quantity of 7/20 multiplying 2 to the power 27 reduced by 1 is the exact signed area under this curve. This curve is always positive, so this would be represented as true positive area, say that segment up here. Well, any questions at all, folks, on that first integration? Okay, so we did a humongous calculation. It just doesn't look like this. That's only because we have really, really powerful theorems working for us. The major results that got us here was the extreme value theorem. A continuous function on a closed interval always has its absolute maximum, absolute minimum, and the mean value theorem. That's what it takes to get to that statement up there. But let's practice with just a few more and try out this one next. So this one is definitely pretty nasty. Just like before, I can't find the antiderivative of x cubed, antiderivative of 7th root of x power 8, and get the correct answer. We need the antiderivative in full, the whole thing at once. But a lot of times you can do a little bit of algebra and get to the right answer that you're expecting. On this problem, it was just exponent rearrangement, and we got where we need to be. This one's similar, but we're really just going to divide, really. So we can all visualize this as integrate from -2 to -1. Let's take that x, divide it into the numerator. It's now x over x plus 1 over x dx. So now we're going from -2 to -1. And that simplifies immediately to a nice constant of 1. And if we were differentiating, we would write that as power -1. We'd have done something along these lines, for example. 1 over x prime is never the quotient rule. We just change the exponent to power -1 and get negative x power -2. But once you get to right here on paper and you're doing an antiderivative, this one is extremely surprising. I will always try to make a big deal out of this because it's really easy to miss. Antiderivative of 1 over x is special, so we should leave that exactly as a 1 over x, so we see the pattern when we go to find that antiderivative. This is the one and only time I wouldn't write this as x as a base in the numerator with some power. Well, any questions at all, folks, to that stage? Okay, we're about ready to get our antiderivatives. I'll go first. Antiderivative of 1 is just an x. Any volunteers for antiderivative of 1 over x? Yeah,
Natural log of x.
absolutely. Thanks for that value there. We get natural log of x. In this problem, we also need the absolute value of it slapped on there so that we can have the most general antiderivative, which also handles these bounds here. Which makes sense because this function, it is defined at -2 to -1. We have a problem right at 0, but our bounds didn't involve it, so we're expecting fundamental theorem to work just fine. But if you've got natural log x without absolute values, we would suddenly have a domain issue with those negative values. So here we're already set to go. And the way I would evaluate this thing has no good special tricks. I can't pull off a constant out of anything on there. So I would visualize it like this. That whole quantity is evaluated from lower limit to -2 to the upper limit of -1. And this is where the process all becomes just a little bit more relaxing. This step is still calculus, so we'd still have to show this on our homework. Take the -1, throw it inside. So now it's -1 plus the natural log of the absolute value of -1. That whole thing is 0, but that's the step we would have to take right there. Here's the minus between the next evaluation. And same thing with the -2. Just throw a -2 inside these things. We definitely want to lead with the extra parenthesis. So -2 goes here, plus the natural log of absolute value of -2. A lot of ofs there to say that. Then all we have to do is simplify this whole thing. So if this was, say, like a 5-point problem, maybe on homework or potentially even on the final exam, I would say right here, doing some of the algebra rearrangements, that is important in this problem. I would probably give that a 1 to 2 points. Let's settle on 1 point. On this stage, you're finding an antiderivative. That's the major part of the theorem. I'd probably call that 3 points. And everything else, to here, I'd call that 1 point. We still have to simplify and get an answer out, but everything beyond here, it's all pure arithmetic from here. So on an exam, if you got to the stage, but made a mistake simplifying it, I probably wouldn't even take off a point. I would just consider that exam stress and that'd be just fine. This is the calculus really right here. But again, on homework, we do take the extra time. We still have to get an answer out of this. So start simplifying it down. We'll have -1 plus natural log of +1 after taking absolute values. Natural log of 1 is 0, so that thing's gone as promised. Then the negative signs will convert this to a positive once it distributes through. So +2 converts the natural log to negative. Now this is natural log of a +2 after doing absolute values. So it looks like altogether on this thing, we're getting 1 minus natural log 2. And we did it, folks. That's the end result on this thing here. Looks like a positive quantity possibly on this thing. And we're integrating this on a negative domain. I don't have a great visual mental picture of that function. I can imagine the vertical asymptote and things like that. But if we wanted to decide how reasonable our answer is, let's say it's like an even numbered question on a homework set, this is definitely a valuable technique. Just go do any graphing utility. Throw in the function. It's f of x equals x plus 1 over x. And we definitely need to manipulate that domain because this picture isn't really doing us any favors. We're going from -2 to -1. So the trick here in this calculator is curly brace -2 less than or equal to x less than or equal to 1. Oh, -1, thanks for mentioning that. And that's our curve right there. Doesn't look anything special, but we're definitely getting positive area. Let's take a look at this. 1 minus natural log 2 comes out as about close to a third on that thing. At this stage, I'd say that all looks really, really plausible. If you took something that was about length 1 for the base, the height on this thing looks like it's about 0.5. So that would have an area of about 0.5 as a rectangle. Cut that in half, it's about 0.25. So in other words, if you want to decide how reasonable the answer is, think of it like this. Huge overestimate of the area right there would give us about 0.5 in area, but that's not our true area. So if you cut it in half, you're about 0.25. Still not completely accurate because we have a true curve here on that thing. But that's what would be my probably best guess if I had to guess on that just by the graph. And we're pretty close just looking at the number there. So you can definitely determine just how reasonable your answer is just by looking at a graph. Spending some time will just decide how much more reasonable it is the longer you look at it. Yeah, go ahead.
In that class, you get to look at the proofs and theorems behind like these, like integral and whatnot.
That would be called elementary analysis. It's a great class. It goes elementary analysis, then it's introduction to real analysis, and then finally analysis is what they're called. So they're undergraduate, graduate level, and then PhD level for each one of those. And basically the way all those classes start is right exactly, no, not that one. They all start right here. They prove these from scratch using epsilon delta type proofs. And then if you can prove these, you're essentially in a great shape to prove just about any property that has to do with differentiation, integration, continuity, because all of those have to deal with limits. So that's where the class where all that kind of comes together. Other questions about that so far? Okay, well, let's keep on going then. So this one, I threw it on here for our just quick set of warm-up problems because it's pretty similar to some stuff that you see in the homework as well. There'll be some derivatives where, integrals where you can do them directly, but these are all ones that you have to do some extra preparation to, similar to what you're seeing in the homework as well. So let's try this out again. After saying that, this one is not one of those kind of problems. This one's essentially a trick question in a certain sense. Let's analyze it the way we would probably do it normally. We need an antiderivative of natural log 3. But if you know the answer right now, you're welcome to just blurt it out. That'd be completely awesome, I'd say, actually. It would be log 1 over 3 on that one. This one's definitely kind of nasty for an antiderivative. Exactly. We'd throw in x. We still have to throw in the natural log 3, but then that's the full antiderivative. Good call. Then if we check that out by taking natural log 3 times x, honestly, that's a tricky derivative on its own too. We have to know that natural log 3 is just representing a constant. There's no real product rule here. I mean, you could use it, but it's unnecessary. The derivative of this would just give you natural log 3. So we've got the right antiderivative the moment we wrote that in. Then if we wanted to, we could leave natural log 3 there, or just do the evaluation on x as we go from 5 to 50. Again, this question is kind of silly on multiple levels. The antiderivative is tricky to find, but again, we don't necessarily have to do any of this on this problem. There is a property that answers this question immediately. Let's keep on doing this, and then we'll think about what that property is and throw it on the notes. So on this evaluation, I have natural log 3 just factored away. I'll just leave it right there. We're throwing 50 inside x. Nothing amazing happens. We just put in 50. Subtract because we're going to the lower limit of integration. Take 5, just plug it right where the x is. 50 minus 5. And now it's natural log 3 times 45. I don't know why, but that always just feels kind of odd. When you put my 45 over here, 45 natural log 3. Now there's no debate what the natural log is, even if you didn't put in parentheses. So that's the end answer on this thing. But again, it's kind of a silly question. If you know natural log 3 is a constant, here's the picture on this problem. We'll put in natural log 3. We're going from 5 less x less than or equal to 50. And natural log 3 has got to be there somewhere. There it is. We're just finding the area under this curve. But it's essentially one really long rectangle, right? So nothing fancy happens. You just need to know what's the width, 50 minus 5. What's the height? Well, the height is literally natural log 3. So this is width times height literally on this problem. Kind of nice in a certain sense, but That's what makes this one nasty. It's hard to find the antiderivative unless we know we're dealing with the constant specifically. But if you know you're dealing with the constant, you don't necessarily need an antiderivative. So the property that answers this question, if we didn't see a graph, is, let's put it on the notes just to combine that thought. It comes from section 5.2. And it's this property right here. If we integrate a constant on a range from A to B, we just look at the width of that range, that's B minus A, multiply it by the constant, and we're in great shape. So that's the property that answers this question. Any questions at all, folks, about this one here? Okay, I can't recall if something like this is in the homework, but I would be suspicious. And I would also watch out for that kind of idea on it, quizzes, or not quizzes, excuse me, on the final exam as well. There might be a couple fast questions where we just have to tell between a constant and something that's really a function. So a question like this, differentiating natural log 3 or times x, or like this could be pretty valid questions. But let's try out another one. We want to deal with a secant squared. I think this is our last one for the set. Then we'll turn to the indefinite integrals. So to get started on this, first thing we need is just an antiderivative. This one didn't have any real trick with it, except that we're dealing with a trig function. So we're evaluating trigonometry again. Any volunteers for what the antiderivative should be? It is tangent. Good call, folks. So the antiderivative of a secant squared is tangent. And on our right, we can write this out, mostly for the sake of notes. Tangent x prime is secant squared of x. So we've got the right antiderivative. We'll evaluate this thing going from pi to 5 pi over 4. And because we know we're doing an evaluation like that, it's not a bad idea to grab out another trig wheel. On the final exam as well, this will be provided. So you don't have to copy that to your notes on the final exam. We're integrating from, let's see, lower limit of pi. So we're down here. We're going up to 5 pi over 4. So that's going to be this radian measurement. And the thing to watch out for, the value of this diagram is, if we integrated to, say, 7 pi over 4, suddenly we have a massive problem here. 3 pi over 2 is in between those, and tangent at 3 pi over 2 is undefined. So these kind of problems that you'll see in homeworks and exams, they're not going to give you a problem that you can't do. But in Calculus 2, we will look at those kind of problems. They'll be called improper integrals of type 1 and type 2. So these kind of thoughts are not bad things to have, just as a good practice for integration. You should always be suspicious about the domain if the problem even makes sense. Here we're in good shape. We're not going across 3 pi over 4, which would cause an undefined. We're only going to 5 pi over 4, and there's no problems there. So at pi, the coordinates here are going to be -1 and 0. At 5 pi over 4, we have coordinates of, let's see, that's got to be √2 over 2. First one is negative. We're in quadrant 3, so is the next one, -√2 over 2. So we've got all of our trig ready to go. Next, we go back to tangent and first throw 5 pi over 4. So tangent at 5 pi divided by 4. Go down to the lower limit, and don't forget the subtraction right here. Do tangent and pi. And we're just about all set. Tangent is sine over cosine. So at 5 pi over 4, you're taking -√2 over 2 divided by -√2 over 2, which is a long way to say 1. So that part's done. Then tangent and pi, any volunteers for this value here? It should be 0, absolutely. It's sine, which is 0 divided by cosine. 0 over -1 is still 0, so it's 1 minus 0. And that means the area under the secant squared curve from pi to 5 pi over 4, if you were curious, is 1. Kind of weird. If you ever get mad at the utility company, you can put this on a check or something like that to represent $1 or something like that. But there we have it, folks. That's kind of our quick rundown on integration after I felt like we just didn't do enough practice when we ended on Thursday's class. Any questions or comments at all, folks, on the end of these problems here? Okay, well, let's put this away. Next, we're going to change gears. We're still finding all of these antiderivatives like tangent x. And all we're really doing is section 4.9 again, but we're throwing new notation on it. So let's take a look at how all that goes down. So the problems we're currently looking at, these are the definite integrals. Now we're taking a look at the so-called indefinite integrals. Let's see if we can put some extra, not too much extra space there. So the idea with an indefinite integral is if f is continuous, capital F is its antiderivative, then here we'll just say antiderivative of f of x, or you could read this out as the integral of f of x, or probably better said, the indefinite integral of f of x. All three things would have the same meaning in this context. But we're looking for a family of functions. We want an arbitrary constant c to be thrown on there. So that's what we mean by an indefinite integral. So we have a couple weird results so far. For example, put this one down. A definite integral gives, let's say evaluates to, that's probably the better language, evaluates to a number. For example, we did a definite integral from pi to 5 pi over, that was 5 pi over 4 of secant squared x dx. And we got a number, exactly 1. But now the next thing we'll say is an indefinite integral evaluates to an entire family of functions. Let's say a family of functions that differ by a constant. And that constant we always refer to as the constant of integration. Usually we put it in as an uppercase C in this context. So a quick example to this one would be, if we do say an indefinite integral, notice right away, we're not going to put any decorations on the integral sign. It's completely vacant. There's no upper limit, no lower limit of integration. And that's the key that tells you this one is indefinite. You're going to get a function indexed by an arbitrary constant. If we did just say x, because it's a good warm-up problem right there, then that x was going to represent the function f of x up here. We find its antiderivative by bumping up the power and dividing by it. So it's 1/2 x squared. Throw in an arbitrary constant of integration. That's the plus c part. And this is what finally an indefinite integral gives us. A whole bunch of functions that all differ by just a constant. In these notes, these are going to be our new notations that we use for antiderivatives going forward. And part of our goal is to get a better feel for what is this saying geometrically really? There's a derivative in there, truly, because if this is the antiderivative, then differentiate that and you get this portion right here, the integrand x. So that's part of our goal as well in these notes. Also, if we keep on scrolling down, we're going to see lots of nice indefinite integral formulas, really antiderivative formulas. First ones are just properties. Antiderivative of a constant times a function is the constant times the antiderivative of the function. We expected that already. We also have the sum law. We have the constant law right here. And then this one is definitely good stuff. We've used this a lot. That's our power rule going in reverse. This one is the exceptional one. Deserves all sorts of extra attention because it's easy to miss that thing when you're learning this subject. But also watch out for some other exoteric things like we're expecting the antiderivative of e to the x to be itself because the derivative of e to the x is itself. But we don't want to lose sight of this one. This one can potentially occur on exams. If it's not e to the x, say a to the x, antiderivative looks similar, but you divide by the natural log of a. And then there's lots of other results we've seen below. One warning though is that this is not an exhaustive list. There are many more results that we picked up along the way. So if you want a better list of derivatives that could be used as an antiderivative, go to this right here, differentiation formulas. It was higher up on the Moodle, but I just walked it down to our current week. And now you can visualize them in this way. Every single formula you see on there, you could write this kind of statement. Let's focus on maybe this one. Antiderivative of cosine x dx is now sine x plus a constant. So every single one of those formulas is really an antiderivative formula at the same exact time. And that's helpful because now all of our formulas have two purposes. We don't have to memorize a new list of formulas just because we're doing antiderivatives. Watch out for things that go, say, like this stuff below. The antiderivatives that are really hard to spot are things like this. Authors supplied this one and this one. They also ask questions that involve all the rest. So keep your eye out for any weird square root functions. If you see a root 1 minus x squared, that's almost a dead giveaway. It's got to be an inverse sine or maybe an inverse cosine. If you see an x thrown on it and an x squared minus 1, that's another dead giveaway. It's probably a secant or cosecant inverse you're dealing with that time. So likewise, for every one of these you see, you could write out antiderivative of -1 x root x squared minus 1 dx. That's just going to be cosecant inverse of x. But don't forget, it still needs the constant of integration c. So those are, again, another set of formulas to be ready to go with. Any questions at all, folks, with antiderivatives down here, visualized as antiderivatives? Well, because I threw the negative right here, I can give it as positive, but good call. We left it like this, and you could expect this in your work. Oh, in the homework I'm referring to rather. If it comes in like this, now you have options. You could put a negative right here, and that would be correct. Or you could even do this. Erasing on this annotate tool is really weird. You could do this, in fact. And that looks more like a secant inverse. So secant inverse of x plus a constant could be thrown in if it goes like that. Well, other questions or comments so far? Okay. Oh, that's actually erase button. Well, let's get back to our section 5.4. So this is a great table, but I think it's more for the more common stuff that you're expected to see and some various formulas as well. But keep in mind that there's much more that can come up on these kind of problems. We'll see as we practice and do homework problems on them. And to start off, we're just going to practice doing some indefinite integrals. Any questions first before we try some random integrals? Okay, instruction says evaluate the integrals. Now let's start off with some decent ones that are pretty similar to what you're going to see in the homework. This one is kind of a nasty one to start off, but it's the good stuff that you want to be familiar with going into a homework question or an exam question. It's the indefinite integral of hyperbolic sine of x minus sine of x. So what you have in black, that's the question. I won't go to blue to solve these. First thing we need is antiderivative of hyperbolic sine. What's nice about hyperbolic sine and cosine is there is never a negative involved. You can differentiate or integrate as much as you like. No negatives emerge. So if you see hyperbolic sine, antiderivative is automatically hyperbolic cosine. So cosh x, and that one's done. But sine and cosine are a little bit tricky. We know the derivative of cosine is negative sine, and now we need the antiderivative of negative sine. Any volunteers for what it should be? Let's go positive cosine, good call. Now on this one, if I was doing this question in exam setting, I'd probably stare at it on the paper, visualize the derivative of cosine itself. That's negative sine. Then I would probably put my eyeball over here and be satisfied. We've got the right thing. It's definitely a good strategy to check as you go when you're writing these things out. Then once we have that, we're still not done. Anyone see what the last step is? Good call. We need that constant integration C. That's something that I personally do forget as well, because sometimes it's a struggle to get through the main problem. Easy to forget about that constant C. But we'll talk a little bit more about it in the class today on what kind of role it also plays. But that's highlight worthy in this section. For doing the fundamental theorem of calculus, I think that negative in the middle is the easy, simple mistake. For an indefinite integral, that's the easy, simple mistake here, forgetting to throw in the constant. But these are some pretty fast problems, so let's try out another one. This will go as antiderivative of root t cubed. Then we have a t minus 1, a t plus 1. And now, since all the variables involve t, I should really write dt here. If I write dx, the answer is everything you see here with the x thrown in. So let's put in dt to make it a normal question. But let's also connect that thought. These symbols really truly matter. If it was written this way, square root of t cubed, t minus 1, t plus 1, dx, that would almost certainly be a mistake on an exam, but if we saw that, here's the right answer. Root t cubed, t minus 1, t plus 1 is now regarded as a constant with respect to integration because we're integrating with respect to x. So because it's constant, we just throw in the x and plus c, and that's the whole answer to that question. Really, really weird. That's a kind of trick question that looks more like an actual typo than what was intended. So that probably won't be on any exams, but it's something to be aware of. Here, if it's dt, we're in business. This one's no trick. But we can't find the antiderivative of square root of t cubed and get the right answer because it's multiplying all this stuff. Really, the only two tools we have to solve this problem are, this is the most important one, it turns out, in this question. We need to break it up. So that's how that expression is indicating. And then, aside from breaking it up, we also need this one. We've used it a lot, but it's always something we have to use very, very carefully to get through the question. So with those two tools, we'll be in great shape. I have a lot. Oh, let's not invert that one though. Control Z to the rescue. I have a lot of extra things to say about this formula. This is a formula that tells us what we've been doing. Just right up here in part A, we've been taking for granted that we can integrate across a negative sign. That's what this is saying altogether. The antiderivative of f of x plus g of x is the antiderivative of f of x, which we put down there immediately as one step, and the antiderivative of g of x. We put it down right there as well. It's a weird formula because we don't necessarily write antiderivative of f of x. We just put it in that spot. So let's do it again for this part B. First thing that happens is, if we want to use this formula, we need to fully expand out to everything we see here. So it's going to begin as indefinite integral. Knowing with what's coming, let's write this as t power 3. It's a square root, so divide by 2. There's truly an index of 2 in that root. Then we can expand out all this right here. That's a difference of squares, so it'll be t squared minus 1 after fully expanding it out. But then we now need to fix this a little bit more. Let me take one extra step to help with the exponents. It's t cubed, or t power 3 halves. The t squared we can write as t power 4 halves. So now when you see 4 halves, that's just power 2 minus 1 dt. Now at this stage, last thing to do is distribute t power 3 halves into the group. Any questions to that stage so far? Okay, let's run the distribution. We now have antiderivative of t to the power. These exponents are just going to add up. So 3 halves plus 4 halves is now 7 halves minus t power of 3 halves dt. At this stage, we're pretty much there. Now we're using this formula right above, and at the same time, we're using the power rule right below it. So let's use both at once. First thing we do is, this part's right here. But we're not going to write another integral sign. We're just going to do it, place the result. So give it a little bit of space before you write the variable t. Add 2/2 to it, so now it's 9/2. Multiply by the reciprocal of 2/9. And that's the power rule here and the sum rule, all used in all at once. And sum and difference rule. So think of this as a plus and negative sign if we want to make it be the exact same format. But same process, a little bit of space after the negative sign. Power is now 5/2. Multiplied by 2/5. I don't necessarily think about dividing by 5/2 or really multiplying by 2/5. The better thought is just put in the right number so that when you differentiate, they cancel off. 5/2 is coming down, we better put 2/5 in there so we get exactly t to the 3/2. Then last thing, or hang on, let me connect this thought. That's this portion of the theorem. We showed that next antiderivative is right here. And then final step, don't let me forget this step, that's a bad one, plus a constant c. If you forgot this on, say, a final exam, you would lose 1 point once. You won't lose 1 point on every single problem. And that's same with the rules about correct limit notation. At most, I'd only ever take out 1 point on a real exam. Well, I think we did it, folks. Any questions or comments with that result here? Okay, then I just noticed the speaker is on. Hang on, let's fix that. It's really weird hearing static suddenly. Definitely don't have tinnitus. Let's try another one. So part C is, let's do this next one. Antiderivative secant theta times secant theta plus tangent theta as a group. And because we indicate a variable theta, we must now use d theta, or else the whole question becomes really, really weird, like we mentioned earlier. Well, just like the problem we did above, I can't integrate part B directly because functions are being multiplied. Down below, it looks even worse. We have trig functions being multiplied, so I would not want to even attempt that thing until we distribute secant theta through that group and see what happens. So first step is really just a distribution. We want the antiderivative of secant squared of theta plus secant theta times tangent theta d theta. And we did use one of these results already. We've correctly found antiderivative of secant squared is just a tangent. So it'll start with the tangent theta. Now secant theta, tangent theta, that one is a derivative of something, and it's kind of a weird derivative. Anyone recall what the derivative would be? Derivative of what function gives secant theta, tan theta? Good call, it's just the secant theta function. So it'll be plus secant theta. So let's double check. Derivative of tangent is secant squared, so I'm happy with the result there. Derivative of secant is secant theta, tangent theta, so that result looks great over here. At this stage, it looks like we have the right function. So let's finish it off with a constant c, and that's the end of this question. Really weird result though, because you have a secant plus tangent theta, resulting in a tangent theta plus secant theta, so the same thing. You just had to multiply it by secant theta to make that go to that. Kind of weird in a way. But we did it, folks. That's another one down. Any questions about these strategies so far? Okay, I don't think I have too many more crazy ones left over. How about one more where we have to divide something just for the sake of extra practice? So let's try out part D. And then we'll take a look at the exercise down below it. So in part D, we're taking a look at antiderivative of root y minus y divided by y squared. Now this has to be written as a dy. Always looks weird putting in different variables, but this could be any variable and it would still make sense. As long as you have the symbol under the root matching this symbol, the symbol being squared, and the dy has the right symbol where y is, it means the exact same thing. But again, I can't necessarily integrate it in this format. even if I was differentiating it, I would probably avoid the quotient rule on this. There's no value in that. You can just divide y squared into everything. And same for antiderivative. So for integration, let's take that numerator. Root y is really y power 1/2 minus y over y squared. I probably could have done more, but that's a good start. We've made all of our exponents a little bit easier to work with. Then on the next step, let's divide y squared into everything. Here I'm putting parentheses, since I need a grouping symbol to say what goes inside. This entire symbol right here wasn't necessary if you had a fraction there. Now, y squared is going to be the denominator to y power 1/2. Let me fix that exponent down below. Because the exponent above is 1/2, let's write it in as 4/2, just to save a little bit of time in redoing those. Here it's going to be minus y over y squared. And here's our next step after cleaning up all those exponents. You want to keep your base y in the numerator, so visualize this one as 1/2 minus 4/2. It'll be y to the power of negative 3/2 altogether. Minus, here, we don't want this one in the numerator. This one is now suddenly the exception to that rule that we just mentioned. Write this one in as a 1 over y, and you'll be in great shape. Then a dy goes here, and all that's left is find your antiderivative, go term by term, and you'll be in all set on this one. Any questions at all, folks, to this stage right here? Okay, so a lot of these problems, they do require a little bit of algebraic manipulation of some kind. A lot of the things you can expect in these sections so far is you might have to FOIL things out, multiply something through a group, divide things through, and that kind of steps. And later on in section 5.5 that's coming up, we'll see how to undo the chain rule. So at the moment, can't get too fancy until we undo that chain rule. It turns out that one's not so bad. Undoing a product rule is worse, and it doesn't even make sense. For differentiation, that was easier, but we're saving that one for calculus 2. That's what they're going to start with, undoing a product rule. But for us, we're going to take this, add 2 over 2 to that exponent. It's y power negative 1/2. The reciprocal of that is negative 2. And if you did multiply, negative 1/2 times negative 2 is a positive 1. Subtract 2 over 2 gets us back to this one. Then go minus because of the minus there. And this one is essentially a very easy formula to forget. It's natural log of the absolute value of y. We need the absolute values on it to make it the most general antiderivative possible. Then throw in the constant. I think on this problem, this is the portion that's highlight worthy. I think that's the trickiest element of this question right here. Well, any questions at all, folks, to this stage? Okay. Again, another thing that's tricky is we definitely want to check this by differentiation. If it was, say, like a real homework problem or an exam setting, if you have extra time, visualize differentiating these things. But if you differentiate this, you're not trying to get back here. You're trying to get back to here instead, right where you had it in the right format to find the antiderivative. So there's some algebra that we might make some simple mistakes on, but whatever you have here, if it's the right antiderivative, I'll always give full credit. So that's a lot of antiderivatives. We've made it to, is that right? A, B, C, D. That was 4 of them altogether. Any questions at all, folks, on getting through these? Okay, let's try out this next problem. Like we mentioned, part of what we'll try to achieve on these notes is give some geometric notion of what an antiderivative is really trying to say to us, what it's providing. So we're going to do example 2 in a way that's pretty similar to what you'll see in the homework. They're going to ask you to prove some formulas that you'll see there. And here's one to start off. It says, prove antiderivative of natural log x is x natural log x minus x plus a constant. Weird, right? This one is not on the list above, but it's a true formula. And there are loads of really bizarre looking formulas like this. It starts to give us a hint on integration is actually kind of hard. There's a really interesting analogy. Think of differentiation as a problem similar to multiplying to the power of 43 or 423, that will work too. To the power of 1030 or 23. It looks bad, but you just take it, put it at base 2 to the power of 423 plus 1203. Let me make sure I put those in right. And that's your answer. It's just a really large number, but you'd be done at that stage. Differentiation is easy in the sense that every function I give you that's differentiable, there is a path. You'll always have the right tools to get there. Integration is much worse. Think of integration as a factoring problem, where we are trying to find all prime factors of something like this to the power of, let's just make it ridiculous. That -1 is the worst part about this. This problem is extremely hard. And if you make this number a little bit bigger, you're starting to get to numbers large enough that this is the basis for your security on systems such as banking online. The reason banking systems are so secure is these numbers are the key to it, and they are extremely hard to crack. So is integration. And this is giving us a hint right here. Antiderivative of natural log is not nice. It's a strange function. Let me put a little border here. But the more we get fluent with integration, the more it does still start to come together. So let's try this out. It's telling us to prove a formula. And this is why I was thinking of these analogies. A question I've had on this is, how did they come up with that? That's a really good question. It turns out it's integration by parts. It's really weird. It can be thought of as a product rule in a certain sense. But all we're doing is checking it out. So let's color code this up. I'm going to think of natural log x as my integrand. So it would be the function we call lowercase f of x. That's the wrong color. Let's go something that will show up. This is the antiderivative, so think of that as uppercase f of x. And let's start by saying let f of x be x natural log x minus x plus the constant. And any kind of problem like this where you're trying to prove an antiderivative formula, this is always the first step. Identify the antiderivative. Second step is just differentiate it right away. We do need the product rule in this thing, and that's why, again, it seems strange, but we are undoing the product rule when we take the antiderivative of natural log x. The reason for that is in the check, you are using that product rule. First, we'll differentiate the x. It transforms into a 1, then copy natural log x. Then there's a plus in the product rule, and the next thing we do is copy down that x, multiply by the derivative of natural log x, which is a 1 over x. Next, just go down the line. Next term is negative x. Its derivative is -1. And that's a constant. Its derivative is 0, but let's put that down there just to be specific. It's weird to differentiate those things that are symbols. Now, here's the whole thing. If we simplify it, it becomes natural log x plus 1 minus 1. And this is our step 3. The moment you write in the last step here, that's natural log x, which is equal to f of x, our work is done. I never actually named f of x. Let me just leave it like this. Equals natural log x, which is the integrand. At that step, the work is completely over. Any questions so far, folks, on doing that check there? Okay, I think for part B, it might actually be helpful for us to define that integrand function. So let's name it lowercase f of x. Let lowercase f of x be equal to the natural log of x. Now, this question down below, in my opinion, it's really, really tricky. Sometimes when I answer this kind of question, I'm not even really sure if I did it right, because integration is going backwards for differentiation. So here's one thought you can have before you even get started with the follow-up question. It says the equation above, that one that we just verified is true, means that the slope of the tangent line to y equals, you have to supply that function at x equals 1 is equal to, you have to supply that number. So let's take a look at this again. we differentiated something, the derivative of this is natural log x. So if we go ahead and plot x natural log x minus x, let's get this back to a decent range as well. Oh, I'm zooming out. Let me go back and zoom in. So let's start with this function, x natural log x. Sorry, having some struggles here. Y equals x natural log of x minus x. So there's our function right there. We differentiate that and got this as a result. So that is the derivative of this function right here. Well, notice there's a horizontal tangent line as well, right, in this location. At x equals 1, we can say what that slope is. Hey, volunteers for the slope right at x equals 1? It must be 0 exactly. So we're plugging 1 either into the function in blue and getting a 0. Doesn't look like that would work, right? That'd be 1 times 0 minus 1. That's not 0 at all. Or we're plugging it inside here and getting a 0. That looks right. Natural log 1 is 0. So I think we're ready to fill out this table. But we're not done with this graph. We'll look at it a bit more. It looks like the slope of the tangent line to y equals, it is going to be x natural log x minus x plus the constant, or it's also indicated as the f of x function, at x equals 1 is equal to natural log 1, which is 0. Let's indicate this one as f of 1 altogether. So, oh, sorry, wrong thing there. Oh, geez. We're here. I got too many windows going on. And here, so I didn't quite put in the right function, though. I put in x, natural log x minus x plus a constant. But the true function should have been, well, it should involve the constant, right? So let's throw in a constant there. We can say put in plus c. Now we're allowing our c to be anything whatsoever. We were visualizing when it was 0. But this is the thing that's kind of interesting about integration. The reason we're getting an arbitrary constant c is because this equation is correct no matter what you put inside there. There's always a horizontal tangent line, whether you go up or down on this thing, choose any real number c, and this whole equation is correct. Well, any questions, folks, about that so far? Okay, so the thing inside is giving you the slope of the tangent line to the output at any value x. That's a tricky problem, so let's carry down those notes and say the integrand which was f of x. I'll write it as f of x so that this is more of an idea for any kind of equation that you'd write in this format here. So the integrand f of x gives the slope to the tangent line of, now it's the antiderivative f of x at any x in the domain. So any x in the domain of both of those functions, if you put in that value here, you'll have the slope of the antiderivatives function at any value x. So again, that's tricky. It's easy to say what the derivative is, but once you throw antiderivatives into the mix, it's easy to get a little bit mixed up with these things. But this could be your one-stop shop to look up these kind of ideas if you ever need to. Well, any last questions, folks, on getting through this one? Okay, what I want to do for class when we come back on Wednesday is put down just one more set of problems. So let's call these tricky problems. I think that's a decent name. So these will be problems that we'll think about, and we'll answer them in full when we come back next class. It's 3 of them, and they all go together. It's going to be, to start, evaluate from 1 to 5 d by dx of root x squared minus 1 dx. So there's problem 1. Problem number 2 says do d by dx of the definite integral from 1 to 5 of the root of x squared minus 1 dx. And the last one we'll take a look at to start us out next class is the derivative with respect to x and Leibniz d by dx of the definite integral from 1 to x of the root of t squared now. So there's no conflict with the integration and upper limit of integration. We'll go t squared minus 1 dt. So every one of these questions can be answered almost instantly, and telling the difference between all three is good evidence that you have great understanding of fundamental theorem of calculus part 1, 2, and the difference between a definite and indefinite integral. So I would say these problems are not only tricky, they're very, very important as well. Well, this will be a good stopping point for us. Give these a try on your own, think about them, and we'll answer them together as a class when we come back on Wednesday. Any questions at all at the moment? Okay, well, have a great night, folks. If I didn't get your exam, it's down below here. And if you're typically coming through Zoom, I do intend to scan these, and I'll have them sent over to you by your email. Well, have a nice night, folks. So we'll see you all on Wednesday.
Taking those analysis classes,
Sorry, say again?
have you taken those analysis
I
classes?
have, yeah. There's something else I have, yeah. I've taken all three, yeah. Elementary analysis is fun. Real analysis is scary hard because I just wasn't ready, but then
Right.
actual real analysis wasn't bad after doing all of that stuff. Any questions? Sure.
Doing this okay so far.
Yeah, you're definitely on the right track. You're
Okay.
doing M5, so it should go 1 through 5,
Mhm.
and your X naught is 0. Delta X is 1/5,
Yeah.
so you'd have a 5th. Yeah, that looks great. Then just keep adding a 5th through. You're on the right track.
Okay, so chicken heart. Thank you.
Mhm.
Down.
I did want to say though, I just forgot,
Uh,
analysis is interesting, but if you ever get the opportunity,
uh,
take a look into complex variables, introduction to
Really?
complex variables and complex analysis later on. I think that's a pretty useful course.
huh, so what is your favorite math book you ever done?
Probably linear algebra topics are
Linear
probably my
algebra?
favorite. Yeah, linear algebra is pretty interesting. It's really hard to explain what linear algebra is really all about because it starts off friendly, you're doing matrices, solving equations,
Mm,
but it's the kind of math class where that type of algebra is everywhere.
Really?
Just about any subject you talk about, linear algebra can probably be pulled in some way. But maybe not Calc 1, Calc 2 so far, but Calculus 3, you do a lot of linear algebra in Calculus 3.
Really?
Yeah,
Yeah, I was hoping to wait to do algebra and special calculus too, but to get lined up, if you do electrical engineering, get lined
Yeah.
up for circuit analysis and stuff.
Mhm.
You're making me do linear algebra right now.
gotcha.
Yeah, which makes me wonder how that possibly integrated into, like, how that applies to circuit analysis and stuff. I have no clue.
When you do circuit analysis, you're gonna have all these nodes, which are gonna apply an equation, that just automatically turn into a huge system of equations.
Huh,
And then you wanna know what are the properties of that? Is there a unique solution?
right.
Is there no solution? Is there infinitely many solutions to this? If all those things could say something good or terrible about your circuit situation.
Would you dive back into, imaginary numbers, and those topics?
That's
Does
a
that
good
happen in
question.
linear algebra?
It doesn't happen much in linear algebra, but it can. It absolutely can.
Because I haven't, because one thing I've noticed was that when I was in high school, I didn't think I'd go to college. I didn't really take math very seriously. And so algebra, I didn't do that well.
Mhm.
I mean, I did okay, I should have paid attention. Now, as I'm doing all this math now, it always comes back to bite me when I get to
Yeah.
algebra principles. I'm hoping that maybe linear algebra will pick up on algebra again.
Yeah, I think definitely.
Imaginary
Oh.
numbers, I don't remember that topic at all.
Isn't that like negative sometimes?
Square root of -1,
Yeah.
yeah. But now that you mentioned it, linear algebra, I made a bold statement, it kind of connects to a lot of stuff.
Uh,
And we're talking about complex numbers, there is an immediate connection.
really?
Yeah, it's kind of strange.
I watched the history of imaginary numbers just really by Veritasium, about how this came about. It's a really cool
Yeah,
video.
Veritasium is amazing.
I
like
love
that guy.
Veritasium.
Let me just find the right thing. Or, yeah, I'm just trying to show you something real quick. That one's a wild ride.
Like help you with talk to, would you help?
I'd be happy to help. Yeah,
Okay.
absolutely. Randy's great, but yeah, I'm always happy to help out. So I'm looking for,
I don't think it was Randy, but I don't know Randy.
sorry,
When you're going semester,
You know, it's like,
you and I have talked to next.
I have calc two, and then he's like, well, after calc two, you can do it now. And I was just like, okay.
Yeah, I don't think so. I was like, shouldn't I take out two first? Just go for it.
That's what he said. I was like, the face you have to do, man. Is
Pretty cool.
high. No.
sorry, I'm drawing a blank on where it is.
No, but I've been getting so interested in math. It's so hard because every time I do a class I'm really interested in, I just want to
Mhm.
finish my degree.
Yeah,
Math is,
I know what you mean.
math is awesome.
Oh, geez, where did it
I've been
go?
watching so much, I think it's Three Blue and Brown. If you ever
Mhm.
watched him.
Yeah, he's
I like-
pretty visual. I love that
Yes,
stuff.
I've been watching this Essence of Calculus series,
Mhm.
which is really cool because I don't know, I watched a little bit before when we first started and it didn't make sense, but now I've done the calculus work, I get it, and now
Mhm.
look at the visualization of it, it's so cool how it applies.
Yeah, I am drawing a blank here.
And then,
It's somewhere in here. I might have to get back to you on
I
that.
see more.
Might be that one now that you mentioned it. No, not quite there.
and then all this stuff.
I know.
Well, it's somewhere in there. Well, if you're curious what isomorphism means, it means just same form. And that's what I was looking for. You can make your complex numbers look like matrices. It
Really?
is really weird, yeah.
Huh,
Not finding the notes, but if you're curious, I can dig it out.
I looked at such interesting, I've looked at so many different math classes, like topography math.
Mhm,
Looks insane.
Topography,
It makes, the
yeah.
whole thing makes no sense at all.
Are you saying topography or topology?
It's a, oh, topology.
Topology
right?
is wild, yeah.
Yes. I've seen people talk about, it's a very far up level math class, right?
It's all about open sets.
Right,
Yeah.
which is completely theoretical, I understand.
It is, but it connects immediately with real world stuff.
Uh-huh.
So a lot of those results in topology, people use in designing like systems or NASA uses to launch satellites and decide
Really?
if they're
That's cool.
got the
They
right
use top-
trajectories. Oh,
That's
yeah.
crazy.
Topology is used quite a lot for that kind of stuff.
Cause every time I look at it, just picking those math classes that you do for the, cause like it is, clearly there's some kind of universal aspect of it, but it's so ridiculous. I don't think there'd be an application of it. I'd like to be.
Mm-hmm. Yeah.
a really theoretical thing.
It's
That's
got
cool.
a ton, yeah. Mhm.
So when the founding fathers of math were doing all this, were they going through these, I mean, they had to, right? They were going through the proofs themselves first and then
Mhm.
come to the conclusion. Which to my understanding, calculus was first discovered like integral, right? Was the first discovered, then it kind of
Mhm.
worked back,
Yeah,
which is how they used to teach calculus, I think.
they
right?
did. Yeah, they used to say integration's easier. We might as well start there. Yeah.
Which is crazy.
But we
Yeah.
turned it all around. I'm not as familiar of why they did integration first.
Well, yeah, I've heard that's how they did it because they discovered it, but I don't even know, I'm not that well versed with that.
Me neither with the history of math,
Right.
yeah.
But it's so cool, just thinking about how the founding fathers got to that point, all theological conclusions, all just,
Pretty much it. The major work that was done was really this guy.
Topology. Everything I see, it looks like it looks like knots, like they tie knots and they use complex spaces. I don't know, it's weird, I don't really get it.
So you've got this guy, Euclid axioms, then you've got axioms of, you could say topology, vector spaces. So the axioms of a topology is just that, nothing more. And then they develop an entire theory out of that. But 2,000 years, well, I'm not even sure, a long time ago, Euclid, these were his axioms, and he did what is considered still to be very rigorous modern geometry, just based off of that and nothing else. So that's what kind of real mathematics starts to look like. The more and more people look back, what Euclid was doing was considered pretty hardcore mathematics.
so
He
cool.
developed a theory as abstract as possible. He didn't even want to look at a bridge. But this is what it's for, to build bridges correctly.
So
But to do that, you abstract away from all the details. You just look at this and prove everything you can get, only assuming those things are true and nothing else.
Oh, that's so cool.
So that's kind of what topology does. Really weird.
Especially like, the one that, the imaginary number one was cool because they're trying to solve, you know, cube roots and like,
Yeah.
cube root stuff, and they kept coming to the conclusion of negative. Cause again, you have to like look at the context, like back in the day with math, they would really think about it like a shape, like you
Mhm.
visualize the geometry of it, and you usually do it the geometrical way, which is way harder than just having like an equation that you plug in.
Yeah, math was not fun back then.
Right, because when they did it, they'd come to the conclusion, they'd come to a negative number, it'd be area, it would match, but then the area they're trying to add up, it'd be negative. So they'd be like, we can't add a negative area. And so they kept going through like cube roots and things like that to figure out why they negative area until one time, finally, I think it's like a French engineer. It's like,
Probably French. They've
yeah,
done a
he-
lot of work.
Yeah, he was like, why don't we just label it an imaginary number? And he did, and he solved those cube root problems, no, he solved it with the imaginary number plugin. And through that, he got actual definite answers on all of them. And that's where imaginary numbers came from. Was
But people were unsatisfied because they had a part of the problem that didn't make sense, but then it gave the right answers. They,
Yeah.
they didn't know what to make of that.
So cool. That is awesome.
Yeah.
Really cool.
Mind boggling my brain and it
That's
hurts.
so, it's so hard when you college, you learn so many cool things, but there's not enough credit. It's kind of tough, you know.
It's
And then
so hard not to think for me,
you can do your thing.
Yeah.
Cool.
but I don't want to do that.
Well, thank you.
Yep, have a good one.